Welcome to another episode of Transparent Physics. In this lesson, we are continuing our series on projectile motion, and the focus of this episode is discussing tips and techniques to help you solve any sort of projectile motion problem that you encounter. By the time we're through with this lesson, you should understand what I consider to be the three tiers of projectile motion. You should be able to organize your solutions into a PAS, a projectile analysis scaffold. And also, I'll provide a word of caution about final velocity in projectile motion problems. One of the most important principles that you can become comfortable with when you're solving problems is to recognize that every problem is not a unique and beautiful snowflake. Usually there are just a couple classes of problems that you could get, and even though they might cosmetically look a little different on the surface, when you peel that away, it's really likely a problem you've already solved. And once you recognize that, you're going to speed up how quickly you're able to figure those problems out. So projectile motion is no different. In my experience, I feel that all projectiles can be broken up into one of three types, and this depends on the angle that they're launched at and their starting height versus their ending height. And when you identify these tiers, it can save you time and effort in your solutions because you're going to know sort of what's coming next and know the shortcuts for the different tiers that's going to help you solve your problem quicker and with less chance of mistakes. As I'm moving into the discussion of tiers, just a quick disclaimer that Tier 1, Tier 2, and Tier 3 are probably not going to show up in your physics textbook or necessarily be mentioned by your physics teacher or professor unless he or she is a fan of the Transparent Physics channel. These are just sort of designations that I've come up with on my own over the years, just as a way to help my students understand the different classes that they're seeing in the wide gambit of projectile motion problems that they could have to solve. So with that disclaimer out of the way, we take a look at Tier 1, the shove. And the shove is just literally that. You're shoving something horizontally, you're kicking it horizontally, you're firing it horizontally, whatever your specific scenario is. The key thing here is that there's no initial vertical velocity. Now that is no initial vertical velocity. The instant it launches, as soon as it's out in the air, gravity is going to be pulling it down. It's going to start acquiring a negative vertical velocity. But at the instant it's launched, and that's a valuable piece of information, it's just going straight out horizontally. If we try to break that up into x and y components using an angle of launch of 0 degrees, in solving for the y component, we're using the sine of the angle, and the sine of the angle is the sine of 0, and the sine of 0 is 0. So again, mathematically, it confirms the idea that there is no vertical velocity at the instant of launch. What we do have is a non-zero vertical displacement. That's a fancy way of saying it falls down, and it ends lower than it started. So your dy value is always going to have some non-zero value, and because it ends lower than it started, the usual convention is going to mean that you result also with a negative value for displacement. So watch out for that when you're solving it. Next up is Tier 2, what I call the punt, classically seen like on a level playing field, and literally it's just like a football being punted. It goes into the air, it comes back down, and the key thing in order for this to happen is that we have to have a non-zero angle of launch, and because it's going to go up and then come down and end at the same height that it started at. And that part where it ends at the same height where it landed out does offer students some confusion, because we'll be talking about one of these solutions and I'll say, hey, dy is 0, that the vertical displacement is 0, and I'll get a question and a student will say, hey, doesn't it go higher than that? I mean, it goes up and then it comes back down, but it definitely went higher than 0. And remember, when we're talking about displacement, and this is a vocabulary issue at this point, displacement means change in position. So if we start, say, at the ground, and we end at the ground, then your displacement is 0. It doesn't matter what you've done. Thinking about it another way, remember, for most days of your life, your displacement throughout the day is going to be 0. You're going to wake up in your bed, you're going to live your life, maybe drive to different states and climb buildings and descend into caverns or whatever you're going to do. And at the end of the day, how far or how little you traveled, you end up back in the same bed, and that's a zero displacement. It doesn't matter how far you went during the day, displacement is your change in position. So if you start and end at the same height, that is a zero vertical displacement. And that's handy for us to remember because that also simplifies our math moving forward. So finally, we get to tier 3, and just disclaimer, you can have a really hard tier 1 problem, and you can have a really hard tier 2 problem, but generally speaking, tier 1 and tier 2 tend to be easier because in each circumstance, there's some initial information that's zero. And whenever there's information that's zero, you can usually simplify your equations and therefore your math moving forward. Dealing with a tier 3 problem, we don't get that advantage. You're launched at a non-zero angle, so the initial vertical velocity is going to be a non-zero value, and also the scenario has a non-zero vertical displacement. And to complicate things even a little further, it could end higher or lower than it started. In a tier 1 problem, you know that your vertical displacement has to be negative. It has to end lower than it started. With a tier 3 problem, you could be higher or lower, so you also have to watch out for whether your displacement is going to be positive or negative as well. And I could fill this entire slide with variations of how it looks. This is one particular example, but it's also a little confusing because the problem can look totally different than the last tier 3 problem you worked, but it still qualifies as tier 3 because, again, it's launched at a non-zero angle and you end at a different height than where you started. Okay, now that we sort of got our identification guide out of the way, now's a good time to pause for a quick sip of tea. And I encourage you to do the same as we move forward now with more practical solution suggestions. Organizing your workspace is perhaps one of the biggest challenges that introductory physics students face when dealing with projectile motion problems because they're faced with a lot more information than they're used to. When solving a one-dimensional kinematics problem, an object rolling along the floor or thrown straight up into the air, there's only 5 possible variables to work with there. You've got displacement, you've got initial and final velocity, you've got your acceleration and your time. And those 5, as you've seen throughout the course, as you've been learning it on your own, are often more than enough to deal with just as is. When we move into 2 dimensions, you've got that now going on horizontally and a matching set vertically, and the vertical set doesn't necessarily have anything to do with the horizontal set, so you've got 2 sets of variables running around, and then also you have to consider the initial velocity itself, which now is a vector quantity, so it's got a magnitude and an angle, and so there's a lot more going on. Not that some of it doesn't simplify with a little bit of insight, but it's still a much steeper climb to get everything organized than it is from earlier in the year. And you might need a little bit of help, so let's get you on the right track. So in order to help us keep organized, I use what I call a projectile analysis scaffold. Again, this is not like standard physics textbook scenarios. If you are in a physics course right now, your professor or teacher may not necessarily show you this format. Doesn't mean that it's not a good technique to use, and I encourage you to think about it because it does help you keep very, very well organized when you're trying to set things up to solve these problems. So you can see going down the left side is your Scooby equations, your kinematics variables. You've got your displacement, your initial velocity, your final velocity, your acceleration, and your time. A couple things of note. It's a double subscript scenario now because we are specifying both initial and final velocity, but we have to be careful about initial and final velocity in the y direction and initial and final velocity in the x direction. So it's a double subscript. Also, the acceleration value in the vertical direction is always going to be equal to g. So instead of writing ay, I just wrote g. Going along the horizontal direction, we've got the acceleration in the x direction, the initial and final velocities in the x direction, and displacement in the x direction. Generally, the area above is where I would write the problem out, And then I saved this large area here for sketch and identifying some of the important visual information. I don't always put as much information labeled in the sketch as I do for a normal problem, because a lot of the information is going to be along the borderline, and I'm not a huge fan of writing the information twice. Okay, leaning in on some of the information we know from episode 1 and the previous slide, the acceleration in the y direction is always going to be negative 9.8 meters per second squared. So just write that in for free. I mean, in theory, you could be solving a problem where you've got something thrown on a different planet. If that's the case, then your g is going to change. But most of your problems will be set here on Earth. Again, unless you're watching this video like 200 years in the future and you're part of a spacefaring race, then you might have to look up Earth's gravity. I don't know how long YouTube's going to be around for. In the horizontal direction, the acceleration horizontally is 0. We talked about with regards to Newton's laws. If there's no forces acting on the object horizontally, there's no acceleration. And the fact that there's no acceleration is going to continue to ripple through this horizontal row and continue to simplify our life. And the reason our life gets a little simpler is because that if there's no acceleration, then there's really no reason to specify an initial versus a final velocity in the horizontal direction, because it's the same thing. If there's no acceleration, the velocity doesn't change. Therefore, we can just say it's the horizontal velocity. It's unnecessary to have more variables than that. Looking at the streamlined projectile analysis scaffold, you can see in the horizontal direction now, there is the acceleration in the x direction equal to 0 meters per second squared. I won't always write that. It's just assumed to always be true in every projectile motion problem you're probably going to solve at the introductory level. The velocities in the x direction have been collapsed into a single velocity because with no acceleration, that value doesn't change. Also, one thing to note is the time. I don't have an x or a y as a subscript there because time is shared between both columns. That's why it sits at kind of the crossroads here. The amount of time it takes to hit the ground is the amount of time it takes to hit the ground. So time often acts as a sort of ambassador between the horizontal and vertical directions to help inform us about how that projectile is moving through the air. And one final piece of advice and caution from years in the classroom, watch out when you're talking about the final velocity, specifically the final velocity in the y direction. I hear a lot of times in my classroom a student will say, well, the projectile hits the ground, so wouldn't the final velocity be 0? And that is absolutely an intelligent thing to say because, I mean, yes, when an object hits the ground or the target, it will come to rest. But we have to think about it in the terms of how we're solving it in the classroom. And we have to follow the same rules for using the kinematics equations that were introduced way back when you first started using them, specifically when you're using the Scooby equations or the kinematics equations. We assume that the acceleration remains constant through the problem. That doesn't mean that you can't solve a problem where acceleration changes, but you're not going to be able to do it sort of in one step. And if an object's moving through the air and then hits the ground, the acceleration as it's moving through the air is different than the acceleration as it hits the ground. And so we would need to break that up into two different parts. And that part of it actually hitting the ground, while often interesting physics, is not really part of the projectile motion experience. So generally, we stop our analysis the instant before it hits the wall or the target or the ground or whatever it's hitting. Like just before impact, we're like, okay, that's good. Another way to think about it would be, think of final velocity as the velocity the projectile would hit you with if you were laying in the target zone. You're not going to be hit with an object moving at 0 meters per second. That's not what a projectile does. So if you would be hit with an object moving with a velocity, then you know that the final velocity is not going to be 0. All right, a couple thoughts to close up this lesson. I get that projectile motion problems can be a lot harder for introductory physics students and maybe more advanced physics students. There's just a lot more information to work with. So a good organized approach can help you handle that information overload successfully. First of all, recognize that when you're solving out projectile motion problems, even though they can appear in a very wide variety, ultimately they probably fall into one of three categories. Identifying that category is going to help streamline your solution and help you recognize some areas where you might be able to zero out some terms and speed your solution along. Secondly, to handle all that extra information, I encourage you to use a projectile analysis scaffold. It's going to help you visualize the information more successfully, and you're going to solve the problem faster. And third, just a general piece of advice, always be careful about talking about the final moments of a projectile motion problem. Generally speaking, stop the problem the instant before it hits, recognizing that it's still moving at impact. After impact, it comes to rest, but most projectile problems are not interested in after impact. They're worried about the flight itself. It's a lot to take in. A big advantage is going to be able to see how each of those work out in practice solutions, and those are coming next in this series. So I look forward to continuing this discussion with you over the course of 3 additional videos for Tier 1, Tier 2, and Tier 3 problems. If you came away from this lesson with a slightly better understanding of projectile motion in general, please consider liking the video. If you have any questions about what I said during the lesson, leave it in the comments. And to find out what's coming next and to help the channel grow, please consider subscribing. And as always, I appreciate you watching this lesson. Projectile motion can be a very confusing topic, and I hope I've made things a little clearer for you on this lesson of transparent physics.